Welcome to my channel Mathematics with Sachin Dikshit. This is the lecture series on replacement problem. This is the second lecture on this replacement problem. In previous lecture, we discussed some basic concepts corresponding to replacement problem. In this lecture, we discuss two theoretical theorems corresponding to this replacement problem. First is replacement of items whose maintenance cost increases with time and money value or scrap value is constant. Then what is the formula? Now how to find the replacement age in this case? And second one is the cost of maintenance of a machine is given as a function increasing with time and its scrap value is constant. If time is measured in discrete units, then the average annual cost will be minimized by replacing the machine when the next period maintenance cost becomes greater than the current average cost. These are the two theoretical parts. Here we use time is measured in discrete units, and in this case time is measured in continuous units. Actually this and discrete units and continuous, these are the two parts of this main article. We discuss one by one all these points. First, replacement of items whose maintenance cost increase with the time and money value or scrap value is constant. Question: the cost of maintenance of machine is given as a function increasing with time and its scrap value is constant. If time is measured continuously, then the average annual cost will be minimized by replacing the machine when the average cost to date becomes equal to the current maintenance cost. We have to derive this formula. This question can also be stated as mathematically: prove that Rn is equals to 1 by n integral from 0 to n rt dt plus c minus s divided by n. For a replacement policy, when n is the best age of replacement or an atom in usual notations, state the conditions under which the equation holds good. This Rn is the maintenance cost at the nth year, and this formula is nothing but average maintenance cost up to n years, and they are equal. Now how it is? We have to derive this. In some cases the question will also ask as in usual notations, prove that Rn is equals to 1 by n integral from 0 to n rt dt plus c minus s divided by n. That means you have to know what is the meaning of these terms, these notations. Now we prove this. Solution: since we have, first we define the terms and their meanings, and then we go to derivation. Since we have t is continuous variable of time, then rt maintenance cost at time t, Rn maintenance cost at time n, C the capital cost of the item, S the scrap value of the item, N the best age of replacement of an item. These are the all notations and their meanings. T is continuous variable of time, RT is maintenance cost at time t, Rn maintenance cost at time n, C capital C the capital cost of the item, S the scrap value of the item, N the best age of replacement of an item. Obviously the annual cost of the item at a time t is given by P is equals to, P is the annual cost. For at the time t, Then first write down maintenance cost at time t, that is RT. Then capital cost minus scrap value means the value of that particular atom at a time t. Therefore, we have to write down here C minus S. Hence, total annual cost of the item at time t is given by P is equals to RT plus C minus S. Since the maintenance cost is increases during n years, maintenance cost is increased during n years and it becomes integral from 0 to n RT dt. Here we take integral because this RT, this time is continuous. Hence we have to take here integral. Therefore, the total cost incurred on the item will be P of n, because it is a function of n. So we have to write down P of n. As time changes, the value will be changes and n is a variable. Therefore, total cost incurred on the item will be P of n is equals to integral from 0 to n RT dt, means the maintenance cost during n years, plus C minus S. C is the capital cost, S is the scrap value. Equation number 1. Hence, the average total cost is given by, this is the total cost up to n years. Hence, to find average cost, just we have to divide n to this equation number 1. Hence, the average cost is given by f of n is equals to P of n divided by n. Just for notation, we have to take average total cost as f of n, and Pn divided by n means we get average total cost. Now substitute the value of Pn, this value in equation 1, and we can write down this f of n, that is average total cost, as 1 upon n integral from 0 to n RT dt plus C minus S divided by n. Equation number 2. Now, to find n such that Fn is minimum. Now, our object is find the value of n such that the Fn, that is average total cost, is minimum. That means it is a problem of calculus. We differentiate Fn with respect to n and equate to 0. In calculus, to find the value of minimum or maximum, we take first derivative and take it is equals to 0 and find the value of corresponding term. That is d by dn of f of n is equals to 0. Now we have to find out the derivative of Fn with respect to n and equate it to 0. But what is the value of Fn here? Fn is 1 upon n integral from 0 to n RT dt plus C minus S divided by n. Now find out its derivative. Derivative with respect to n. Remaining all terms are constants. We have to find out derivative with respect to n. In the first term is 1 upon n integral 0 to n RT dt. There are two terms of n. One is 1 upon n, other is integral from 0 to n RT dt. Apply product rule. First 1 upon n as it is, and derivative of this integral from 0 to n RT dt is nothing but Rn. Derivative and integration are opposite process, hence its derivative is Rn. Plus, now that integral kept as it is, and find out the derivative of this 1 upon n. Derivative of 1 upon n is minus 1 upon n square. Plus, now in the second term, C minus S divided by n. C minus S is constant, kept as it is, and derivative of this 1 upon n is again 1 upon n square, which is equals to 0. Now just simplify this. Some simplification will be takes place, and we can write down this as 1 upon n Rn minus 1 upon n square integral from 0 to n RT dt minus C minus S divided by n square is equals to 0. Then multiply by n to whole bracket, whole term, whole equation. We get Rn, because if we multiply by n, then n gets cancelled. If we multiply these two terms by n, then this n square becomes n. Hence, we get an equation as Rn minus 1 upon n integral 0 to n RT dt minus C minus S divided by n equal to 0. And now just transfer these negative terms from LHS to RHS. We get expression as Rn is equals to 1 upon n integral from 0 to n RT dt plus C minus S divided by n. This is not applicable. Equation number 3 not equal to a equal to 0. Now if we observe this equation 3, this term 1 upon n integral from 0 to n RT dt plus C minus S divided by n is nothing but the value of f of n. That means we have to show that here as Rn is equals to f of n. Therefore Rn is equals to f of n. But what is f of n? F of n is average total cost, that is Pn divided by n. Hence we have the maintenance cost at time n, that is Rn, is equal to the average total cost, that is f of n, in time n. Thus, the cost of maintenance of a machine is given as a function increasing with time and its scrap value is constant. And if time is measured continuously, then the average annual cost will be minimized by replacing the machine when the average cost to date becomes equal to the current maintenance cost. This is the first theoretical part. Now come to the second one. The cost of maintenance of a machine is given as a function increasing with time and its scrap value is constant. These two conditions are the same which are in the previous case. If time is measured in discrete units, in first theoretical part their time is measured in continuous units. Here time is measured in discrete units. Then the average annual cost will be minimized by replacing the machine when the next period maintenance cost becomes greater than the current average cost. This is statement in word format. In mathematical format, this statement can also be written as, in usual notations, prove that Rn is less than Pn upon n less than Rn plus 1. Rn is maintenance cost at nth year and Pn upon n is the average maintenance cost. Average annual cost is Pn upon n, and this Rn plus 1 is next period's maintenance cost. And here we have to show that this average annual cost is greater than the current average cost. Next period's maintenance cost, that is Rn plus 1, is greater than current average cost, that is Pn upon n. And then in that case we replace the machine up to after n years. For the replacement policy for the items whose maintenance cost increases with time and money value constant, then n is the best age of replacement of an item. Now we prove this. Again we have to first mention the variables and their meaning in this theoretical part. Proof. Let t be the discrete variable of time. RT, maintenance cost at time t. C, capital cost of the item. S, the scrap value or money value of the item. N, the best age of an item. You may take n is not capital, it is a small n. N is the best age of an atom. Small n is the best age of an atom. Since the time is considered in discrete units, then the maintenance cost during n years becomes summation t varies from 1 to n RT. It is this time unit is described in discrete units, hence we take summation. If they are continuous, we can take it is in the integral format. But here discrete units, so we take the summation. the total cost of the item during n years will becomes P of n is equals to summation T varies from 1 to n RT plus C minus S. Equation number 1 is the total cost on the item during n years. Hence, the average total cost is given by f of n is equals to Pn divided by n. Now substitute the value of Pn. Therefore, f of n is equals to 1 upon n summation T varies from 1 to n RT plus C minus S divided by n. Equation number 2. Now, by using finite differences, Fn will be minimum if del f of n minus 1 is less than 0 is less than del f of n. This is the formulation for minimization. Finite differences, del fn will be minimum if del of f of n minus 1 is less than 0 is less than 0 less than del f of n. Equation number 3. Now we use this finite difference method. First we take this part 0 is less than del f of n, and then we consider del f of n minus 1 less than 0, and then lastly we combine these two results. We go one by one. Then by definition we have del f of n is equals to f of n plus 1 minus f of n. Now we know the value of f of n. By using this f of n, we can find out the value of f of n plus 1. And we put here. We get it is del f of n is equals to p of n plus 1 divided by n plus 1 minus p of n divided by n. Now substitute the values of p of n plus 1 and p of n. We get del f of n is equals to 1 upon n plus 1 into bracket summation T from 1 to n plus 1 RT plus C minus S minus 1 upon n into bracket summation T varies from 1 to n RT plus C minus S. Then we multiply this 1 upon n plus 1 in this bracket and this multiply this minus 1 upon n to this bracket. We get the expression as 1 upon n plus 1 summation T varies from 1 to n plus 1 RT plus C minus S divided by n plus 1 minus 1 upon n summation T varies from 1 to n RT minus C minus S divided by n. We multiply this minus 1 upon n, so this term will be negative and this term will be negative. Now, we make adjustment in this first term. We split up this summation and we remove one element corresponding to this summation as r of n plus 1. This summation T varies from 1 to n plus 1 RT can be written as summation T varies from 1 to n RT plus Rn plus 1. And then we split up this 1 by n plus 1 to both the terms and we get 1 upon n plus 1 summation T varies from 1 to n RT plus 1 upon n plus 1 R of n plus 1. And this second term 1 up minus 1 upon n summation T varies from 1 to n RT take as it is. And these two terms C minus S divided by n plus 1, C minus S divided by n. Take C minus S common from both, then we get plus 1 upon n plus 1 minus 1 upon n C minus S. Now, here it is summation 1 to n RT, here also summation 1 to n RT. Take that summation common, then we get in the bracket 1 upon n plus 1 minus 1 upon n into summation T varies from 1 to n RT plus this middle term as it is and this last term as it is. Now if you observe the first and last term, the square bracket 1 upon n plus 1 minus 1 upon n is again same. Take that term common, we get the expression as 1 upon n plus 1 minus 1 upon n into summation T varies from 1 to n RT plus C minus S plus 1 upon n plus 1 R of n plus 1. Now, what is this value? This value is nothing but P of n. This value is nothing but P of n. We substitute here. But before that, we take this term as a first term and we cross multiply here, we get n minus of n plus 1, just cross multiplication, divided by n into n plus 1, and remaining term in the bracket as it is, that is summation t varies from 1 to n rt plus a c minus s. But what is this value? This value is nothing but p of n. We put here, and we multiply this minus sign to this bracket, therefore this is minus n, and this minus into plus, that is minus. Now in this case, plus n minus n gets cancelled out. Just simplification, it gives minus 1. Then take that minus sign in the middle. We get the expression as Rn plus 1 divided by n plus 1 minus Pn divided by n into n plus 1. As del f of n is greater than 0, we have, this is the value of del f of n, this value is also greater than 0. Then this negative term will transfer. Then we get Rn plus 1 divided by n plus 1 is greater than Pn divided by n into n plus 1. In both the term there is n plus 1, n plus 1. We cancel out that term. We get R of n plus 1 is greater than Pn upon n. Equation number 4. Remember this equation. At the last we have to combine this result. Now consider the second case. Similarly, we have del f of n minus 1 is equals to f of n minus f of n minus 1. Substitute the values of fn and fn minus 1. We get pn divided by n minus p of n minus 1 divided by n minus 1. Now again substitute the values of pn and pn minus 1. We get 1 upon n summation into bracket summation t varies from 1 to n rt plus a c minus s bracket complete minus 1 upon n minus 1 into summation t varies from 1 to n minus 1 rt plus c minus s. Now again multiply this 1 upon n to this bracket and minus 1 upon n minus 1 to this bracket. We get the expression as 1 upon n summation t varies from 1 to n rt plus c minus s divided by n minus 1 upon n minus 1 into bracket t varies from 1 to n minus 1 rt. Then multiply this, therefore we get minus c minus s divided by n minus 1. Now in the first case there is summation t varies from 1 to n plus 1. Therefore there in that case one term will be more but here t varies from 1 to n minus 1. So one term here is less. We have to add that term, that is Rn. In this summation we have to add Rn, and so this summation becomes 1 to n, and one term Rn we have to adjust here, means plus Rn minus Rn. That plus Rn will be added to this and minus Rn will be separate out, and then multiply this bracket, but that minus and this minus becomes plus, and hence the expression will be 1 upon n summation t varies from 1 to n rt minus 1 upon n minus 1 summation t varies from 1 to n rt. That we have to adjust here. We have to add here Rn term and then subtract one Rn term, and that subtracting term is minus, and this outside minus, that minus minus becomes plus. Hence it is plus 1 upon n minus 1 Rn. And from cs upon n and cs upon n minus 1 we take c minus s common, and in the bracket we get 1 upon n minus 1 upon n minus 1 into c minus s. Now again combine this summation Rn terms. We get into bracket 1 upon n minus 1 upon n minus 1 into bracket summation t varies from 1 to n rt plus 1 upon Rn minus 1 upon n minus 1 Rn plus into bracket 1 upon n minus 1 upon n minus 1 c minus s. Now again first and last term, if you observe, the some term will be common, that bracket square bracket will be common. Take that common, we get del f of n minus 1 is equals to into bracket 1 upon n minus 1 upon n minus 1 into bracket summation t varies from 1 to n rt plus c minus s plus 1 upon n minus 1 Rn. Now again this summation is nothing but P of n. We put that value, but before that we have to cross multiply here. Then we get n minus 1 minus n, and divide by n into n minus 1. Remaining terms will be the same. Then we put this value as Pn, and in this square bracket plus n minus n gets cancelled out. Remaining term is minus 1 only. Then take this minus at the middle. We get del f of n minus 1 is equals to Rn divided by n minus 1 minus Pn divided by n into n minus 1. As del f of n minus 1 is less than 0, we have this total term is less than 0, that is Rn divided by n minus 1 minus Pn divided by n into n minus 1 is less than 0. That implies Rn divided by n minus 1 is less than Pn divided by n into n minus 1. That n minus 1 gets cancelled out, and we get Rn is less than Pn upon n, equation number 5. And in equation 4 we have to show that this Pn upon n is less than Rn plus 1. Now we combine these two results. Hence from equations 4 and 5 we have Rn is less than Pn upon n is less than Rn plus 1. Hence, the total cost of maintenance of a machine is given as a function increasing with time, and its scrap value is constant. If the time is measured in discrete units, then the average annual cost will be minimized by replacing the machine when the next period maintenance cost becomes greater than the current average cost. Now, one more point we have to discuss in this case, that is useful deduction. That is, in solving the numerical problem, to compare the average, it is sufficient to compare the average cost only. Average cost only. This is because the replacement policy which we have to derive here previously, Rn plus 1 is greater than Pn upon n, where Pn is summation t varies from 1 to n Rt plus c minus s, can be easily shown to be equivalent to Pn plus 1, P of n plus 1 divided by n plus 1 is greater than P of n divided by n. Means to check this replacement policy, it is equivalent to check this average costs only. If we compare average cost, automatically this condition will also be satisfied in that problem. In numerically, when we take some problems of replacement, we can check out in that case, but this will be exist, that is useful deduction. Both these inequalities are equivalent. Hence, we have to check out this equality, how it is equal. We start with this inequality and we come to this inequality. How? We start with the part. Since P of n plus 1 divided by n plus 1 is greater than Pn upon n. Now substitute the value of Pn plus 1. That is 1 upon n plus 1 into summation t varies from 1 to n plus 1 Rt plus c minus s. Then one term will be here excess. We have to split that term. Therefore, we get summation t plus t to n Rt plus r of n plus 1 plus c minus s is greater than Pn upon n. Now, collect the term 1 upon n plus 1 into bracket summation t varies from 1 to n Rt plus c minus s in one bracket, and next is plus Rn plus 1 is greater than Pn upon n. Now this bracket is nothing but P of n. We get 1 upon n plus 1 into bracket Pn plus Rn plus 1 is greater than Pn upon n. Now cross multiply this n and this n plus 1. We get n into Pn plus R of n plus 1 is greater than n plus 1 into Pn. Now multiply this n and multiply this Pn to this bracket. We get nPn plus n into Rn plus 1 is greater of n into Pn plus Pn. We have to check out this Rn plus 1, take as it is, and transfer this np of n. We get n Rn plus 1 is greater than npn plus pn minus npn. This np of n and this np of n will get cancelled out, and the remaining term is n into Rn plus 1 is greater than p of n. Now just divide by this n, we get Rn plus 1 is greater than pn upon n. Hence, this inequality p of n plus 1 divided by n plus 1 greater than p of n divided by n is equivalent to r of n plus 1 greater than p of n divided by n. This will be exist. We have to check this when we solve some problems on the replacement. We solve some more problems of replacement in the next lecture. These are the some reference books corresponding to this lecture. We have to take the points corresponding to these reference books. Thank you for watching this video.